Hi everyone, welcome to the advanced section of Unit 1. In this unit we're going to take a look at SI units. These are the numbers and measurement systems that we use in science to make our measurements and communicate with other scientists. All the scientists agreed, yes, we should use this system so they can all communicate with each other effectively. Now there's a bunch of different dimensions that we can measure. We can measure force, we can measure distance, we can measure time, we can measure mass, we can measure current, we can measure a whole bunch of things. But most of them are based off of three base units that we use over and over and over again. And these measure three common dimensions. The first one is mass, which is how much matter is in an object. This is how many protons, neutrons, electrons are packed into it. It is not a measure of how strongly gravity pulls on it. That's what weight is. This is dependent on gravity. Mass is just how much matter, how much stuff it's made out of. The SI unit we use for mass is grams, which has symbol lowercase g. Grams are fairly small, so sometimes we use a bigger unit. It's still a gram, but we put a kilo in front of it. We'll talk about what that means in a minute. Kilograms, which would be kg. Another common unit that we use a lot is length, and that's the distance between two objects. You guys know what length is. The SI unit is meters. That would be a lowercase m, and anything that has the prefix in front of it, like centimeters, kilometers, those are measurements of length. The last one that you're familiar with is time, and that is just measured in seconds. So everybody uses seconds. That's not strictly an SI unit. It's also our standard unit. So when we start combining units or doing math with units, we have to pay attention to a couple things. When we're adding or subtracting units, those units have to match. And that's because it does not make sense to say something like, let's add 15 seconds to 12 meters. This is measuring how far something's gone. This is measuring how long it takes. We can't add those. Units have to match. Even if they measure the same thing, like 15 centimeters plus 12 millimeters. This is like adding feet to inches. Yes, they both measure length, but they do it in a different way. 12 feet plus 12 inches is not 24 feet, it's 13 feet. 15 centimeters plus 12 millimeters is not 27 millimeters or centimeters, it's 16.2 centimeters. So we have to make sure our units match before we can add them with addition or subtraction. However, that same rule is not true for multiplication and division. They do not need to match to multiply and divide units. And when we multiply and divide units, we end up with these things that are called derived units. And we call them derived because they're made from the base units. So if you have speed, which is measured in meters per second, it's actually a distance divided by a time. Its unit is meters per second. That's a derived unit. If you have density, density is mass divided by volume, which would be kilograms divided by cubic meters. You'll notice this cubic meter, that's actually a meter times a meter times a meter, because when you find the volume of a shape, you have to take its length times its width times its height. Those are three dimensions, three lengths. You multiply them together, you get cubic meters, so that's a derived unit. And then you'd have a kilogram on top of it because how much mass is in this thing. Now we have density, that's a derived unit. So it doesn't matter what the units are when you have multiplication and division, you just have to keep track of them. This is called a derived unit. Now, we can actually use different SI prefixes to make really little numbers look more manageable, or really big numbers look more manageable numbers. And basically, SI prefixes, which you guys are familiar with, they're down here, kilocent, milli. These are just fun ways, shorthand ways of using scientific notation, or powers of 10. I'm sure you guys have seen 1.7 times 10 to the fourth. What does that mean? Well, this power of 10, this positive 4, says the decimal point really needs to move 4 places in a positive direction, or to the right. So 1.7, we hop this decimal 4 places over, that's 17,000, and these two numbers are the same. So 1.7 times 10 to the fourth, 17,000 are the same, because we move the decimal 1, 2, 3, 4 places right. You can also move it left. That's what a negative indicates. So if I add 4.3 times 10 to the negative third, this negative 3 says, oh, I need to move the decimal point 3 places left. So I'd go 1, 2, 3, and I'd have 0.0043. So that's scientific notation. It just allows us to write small numbers or big numbers more simply. And these are kind of silly examples, but one of the numbers that people use in chemistry is called Avogadro's number. It's 6.02 times 10 to the 23. That's a 602 and then 21 more zeros. And nobody wants to write zeros forever and ever and ever and ever and ever. They just come off the page. So that's why scientific notation is handy. And because we use these quite frequently, we do have some common names for them. So kilo is times 10 to the 3. So kilometer really means, so if I had 2 kilometers, say, I really have 2 times 10 to the 3 meters. I replace the kilo with the times 10 to the 3, and that's what I have. So this is 2,000 meters. So that's why we say kilo means 1,000. Kilo is times 10 to the 3, which is 1,000. And centi means 100th. So if I had 89 cents, I would have 89 or 89 centimeters, then I'd have 89 cm like that, and I can replace that c with the times 10 to the negative 2, 89 times 10 to the negative 2, and that gets me 0.89, and I still have my meter there, meters. So it's 0.89 of a meter, or 89 hundredths, 89 cents of a meter. And then milli, same thing, this is times 10 to the negative 3, so it moves the decimal place one more further than the centi. Alright, so we can use those to make our life easier and write big numbers as small numbers and small numbers as not so small numbers, but we have to be careful because we have to make sure our units match before we combine things. So we actually change prefixes back and forth depending on what we need to get done. So right here I have a list of common prefixes, three places either direction of base. So base is grams, seconds, meters. There's no prefix in front of it. Centimeters, millimeters, decimeters if we're going smaller, or deca, hecta, and kilo. Now hecta, deca, and deci are almost never ever used. I'm just putting them here for placeholders, so we do have all these names. Mostly that's because it gives you an easy way to convert from or to a base unit. So like this says take 18 centimeters and make it into meters. So if we do that, this centimeter is over here. Here's my C, and I want to go to base, which is in the middle. That's 2 places left. So that means take my decimal point and move it 2 places left, which gets me 0.18 meters. The other way you can think about that is this centi means times 10 to the negative 2, so 18 times 10 to the negative 2 meters is 0.18 centimeters. Same thing here. I want to go from grams to kilograms. Well, grams is actually base. Kilo is over here, so I'm going to start at base and I'm going to go 1, 2, 3 places left. So 1, 2, 3 places. This is 0.020 kilograms. Those are the same thing. And then 700 millimeters to meters. Millimeters is over here. 1, 2, 3 places to base. So this becomes 0.700 meters. And then finally 12 kilometers to meters. We've got kilometers over here, and base meters are here, so 1, 2, 3 places to the right. This is 12,000 kilometers. So if you have to take 14 centimeters plus 10 millimeters, that's a little bit hard to do because they don't have the same units. But if I want to go from milli to centi, that's 1 place to the left. So I can take 14 centimeters plus 1 place left, 1.0 centimeters, and that gets me 15 centimeters. So now I can combine those because I made their units match.